In 1250 CE, 20 million rats begin eating the seeds of a palm forest on a volcanic island the size of Washington, D.C. The forest will take 300 years to die, and nobody alive on the island during those centuries will notice it happening. 700 years later, a NASA-funded mathematician writes 4 differential equations on a laptop and watches that same island collapse on screen. He changes one set of numbers and watches modern civilization collapse the same way. Within 72 hours, NASA publicly disowns the paper. And right now, beneath the Texas Panhandle, water that fell as rain 10,000 years ago is being pumped out at 18 Colorado rivers per year to grow food that will be eaten this week. Those are the same story, the same 4 variables, the same coupled differential equations, the same threshold past which recovery becomes mathematically impossible. And the part that will keep you here tonight is not the math itself. It is what the math says about who feels the collapse last, and why those are the exact people who would need to act first. If you are new here, subscribe or join. If you want the broader work across physics, systems collapse, and the mathematics most channels will not touch, that lives on Patreon. Stay through this one, because by the end, you will know the exact parameter that determines whether a civilization's curve levels off or crashes, and you will know what our current value is. Let's start where it started. In 2014, a mathematician at the University of Maryland sat in front of his computer and watched a civilization die. Not a real one, a simulated one. 4 equations running on a laptop: population, natural resources, accumulated wealth, and the split between elites and commoners. He had written the equations himself, a young applied mathematician named Safa Motesharrei, working under the supervision of Eugenia Kalnay, one of the most cited atmospheric scientists alive. The model was elegant in the way that mathematics is elegant when it describes something terrible. 4 coupled, ordinary differential equations, the kind of system a second-year math student could write on the back of a napkin. And when Motesharrei calibrated the parameters to match a small, isolated island civilization that had destroyed its own resource base and collapsed, the model reproduced the collapse perfectly. Population overshoot, resource depletion, a brief golden age followed by a fall so steep the curve looked like a cliff. Easter Island, Rapanui, the most famous cautionary tale in human history. But that is not why I am telling you this. I am telling you this because of what Motesharrei did next. He changed the parameters. He scaled up the resource base. He increased the population. He adjusted the regeneration rates and the depletion rates to match modern industrial civilization. Global scale: 8 billion people, fossil fuels, fresh water, topsoil, fisheries, forests. He ran the simulation, and the curves were the same, not similar, not analogous, mathematically identical in structure. The same overshoot, the same lag between depletion and awareness, the same point of no return that the system crosses silently without anyone noticing, because the people at the top of the wealth distribution are insulated from the consequences until the collapse is already irreversible. That model was published in the journal Ecological Economics in 2014. It was partially funded by a NASA Goddard Space Flight Center grant, and within 72 hours of the press coverage, NASA issued a formal statement distancing itself from the paper's conclusions. Not because the math was wrong. Nobody challenged the math. NASA simply said it did not endorse the paper or its conclusions, a funding agency publicly disavowing the implications of research it helped pay for. Think about what that means. Think about the kind of conclusion that makes a government agency step in front of cameras and say, "We do not want our name on this." The paper is still there. The equations still work. The curves still match. And the resource depletion rates Motesharrei used for his modern civilization parameters have, in the 11 years since publication, gotten worse, not better. Every single one. That is what this is about. Not the fairy tale version of Easter Island, where foolish people cut down trees because they were too dumb to see what was happening. That version is wrong. The real story is worse. The real story is that the people of Rapanui were not stupid. They were not blind. They were trapped inside a mathematical structure that made rational individual decisions produce collective suicide. And the mathematical structure they were trapped in is the same one you are trapped in right now. The same equations, the same variables, the same dynamics, the same outcome, unless the parameters change. And the parameters are not changing. To understand why the math works the way it does, you need to understand what actually happened on Easter Island. Not the Jared Diamond version, not the version where tens of thousands of people waged cannibalistic warfare over the last scraps of a paradise they had mindlessly destroyed. That version makes for a compelling TED Talk, but the archaeology tells a different, and in many ways more disturbing story. Start with what the island looked like before humans arrived. Rapanui sits in the southeastern Pacific, roughly 3,700 kilometers from the Chilean coast and 2,100 kilometers from the nearest inhabited island, Pitcairn. It is one of the most remote pieces of inhabited land on Earth, 163 square kilometers. For scale, that is roughly the size of Washington, D.C. When Polynesian voyagers first reached it, sometime around 1200 CE, based on the most reliable radiocarbon dating from Terry Hunt's work, the island was covered in a dense, subtropical forest. The dominant species was a palm closely related to the Chilean wine palm, Jubaea chilensis, which can grow up to 25 meters tall with a trunk diameter of over a meter, and which, critically, takes approximately 70 years to reach reproductive maturity. 70 years, a human lifetime to grow a single tree capable of producing seeds. Pollen core analysis from the crater lakes at Rano Kau and Rano Raraku, first conducted by the paleontologist John Flenley in the 1980s, and refined by subsequent researchers over 3 decades, shows palm pollen constituting 40 to 70% of all pollen deposited during the centuries before human arrival. The island was not just wooded, it was dominated by a single species of massive palm in a way that made the entire ecosystem dependent on that one tree. The palms stabilized the soil, they moderated the microclimate, they provided habitat for nesting seabirds, they produced a sugary sap that could be fermented. Their wood provided material for canoes, which provided access to deep water fish. Remove the palm, and you do not just lose a tree. You lose the soil, the birds, the rain interception, the canoes, the deep sea protein, the building material, the fuel. The entire web unravels from a single thread. In 2010, Andreas Meath and Hans Rudolf Bork at the University of Kiel published a paper in the Journal of Archaeological Science that changed how we understand the scale of what was lost. They did something nobody had done before at that resolution. They dug soil trenches across the island and mapped the charcoal layers, the burned palm stump remnants, and the charred palm endocarps, the hard inner shells of the palm fruit. Their estimate was staggering. More than 16 million palm trees had once grown on the island, covering roughly 70% of the land surface, about 116 square kilometers, 16 million trees, and nearly all of them were gone by the 1500s, 3 centuries 16 million trees to 0 in 3 centuries. Let me give you a sense of that rate. That is roughly 53,000 trees lost per year, or about 145 per day every day for 300 years. If you could have stood on the ridge above Rano Raraku and watched in time-lapse, the forest would have retreated like a tide going out. And the pollen record confirms exactly that. The transition from palm-dominant pollen to grass-dominant pollen in the crater lake sediments is not gradual. It is steep. The forest did not thin gracefully. It collapsed. But here is where the standard narrative starts to crack. The assumption has always been that the Rapanui cut them all down to transport the moai, those massive stone statues that have become the global symbol of the island. Jared Diamond, in his 2005 book Collapse, built his entire Easter Island chapter on this chain of reasoning. Statue cult drives deforestation. Deforestation drives ecological collapse. Ecological collapse drives warfare and cannibalism. Simple, clean, satisfying as a narrative, and probably wrong. Diamond estimated the peak population at somewhere between 15,000 and 30,000. He described a society driven to cannibalism by ecological devastation of its own making. He presented it as the clearest example of a civilization committing ecological suicide, and the image was so powerful, so useful as a parable, that it became the canonical version. Every environmental speech, every climate documentary, every sustainability course. Easter Island, the place where they cut down the last tree. But the archaeology kept accumulating, and the archaeology disagreed. In 2011, Terry Hunt at the University of Arizona and Carl Lippo at Binghamton University published a book called The Statues That Walked, and they backed it with something Diamond never provided: experimental evidence. Their analysis of the moai that had fallen along the ancient road corridors leading from the Rano Raraku quarry revealed something the sledge hypothesis could not explain. The bases of the road moai were not flat. They were D-shaped, carved with a deliberate forward lean of 6 to 15 degrees from vertical. If you were dragging a statue horizontally on a sledge, there is no reason to carve a rounded, tilted base. But if you were walking the statue upright, rocking it from side to side, the way you might walk a refrigerator across a room, that base geometry is exactly what you would engineer. The roads themselves provided the second piece of evidence. They were not flat tracks suitable for sledges. They were concave, slightly cupped, about 4.5 meters wide, perfect for a rocking, walking motion, terrible for a sledge. In 2012, they proved it. They attached 3 ropes to a 4.35-ton concrete replica of a moai, and an 18-person team walked it 100 meters in 40 minutes. No trees required, no sledge, no rollers, no army of laborers hauling timber. 18 people and 3 ropes. The Rapanui oral tradition had said it all along, for centuries, to every anthropologist who asked. How did the moai get from the quarry to the platforms? They walked. The moai walked, and the anthropologists wrote it down as mythology, as charming native legend. They did not test it because they assumed they already knew the answer. The statues were too heavy to walk. Therefore, the natives were remembering wrong. Therefore, they must have used log rollers. Therefore, they must have cut down the forest. In 2025, Lippo and Hunt published a follow-up in the Journal of Archaeological Science, validating the walking hypothesis against additional archaeological evidence and responding to critics. The evidence has held up for 13 years. The moai walked. This matters enormously because it removes the central gear from Diamond's machine. If the moai did not require massive timber infrastructure, then the statue cult alone cannot explain the deforestation. And if the statue cult alone cannot explain the deforestation, then the story is not about stupid people destroying their environment in the pursuit of vanity. The story is about something else entirely, something that does not have a single villain or a single moment of folly, something more systemic, more structural, more mathematical. So what did destroy the forest? Hunt and Lipo pointed to an accomplice that arrived with the first Polynesian canoes, but has received almost no attention in the popular narrative. Ratus exulans, the Pacific rat, a small, brown, omnivorous stowaway that the Polynesians carried, intentionally or not, on every voyage across the Pacific. Based on reproductive rates and available food supply, Hunt estimated that the rat population on Rapanui could have exploded to as many as 20 million individuals within a few decades of arrival. 20 million rats on an island the size of Washington, D.C. And those rats ate palm seeds. When Hunt's team examined the collection of preserved palm endocarps at the Sebastian Englert Museum on the island, they found that virtually every single one showed gnaw marks consistent with rat teeth. The palms were not just being cut, they were being prevented from reproducing. The rats ate the seeds before they could germinate, and since the Jubea palm takes approximately 70 years to reach reproductive maturity, the math is devastating. You do not need to cut down every tree to destroy a forest. You just need to eat every seed. The forest does not die suddenly. It dies slowly, one unborn generation at a time, while the adult trees are still standing. The living forest becomes a ghost forest, a population of aging individuals with no children, standing tall and green while its future has already been consumed. I want to stop here for a moment, because this image, the ghost forest, is going to become important later. A system that looks healthy on the surface because the visible indicators are still intact, while the regenerative capacity, the part you cannot see, has already been destroyed. The canopy still green, the seeds already eaten, everything fine until the last adult tree falls and nothing grows to replace it. Remember that image. It is going to haunt the rest of this story. But the rat hypothesis does not let the Rapanui off the hook entirely. And this is where the honest version of the story gets more uncomfortable than either the diamond version or the Hunt and Lipo version taken alone. Mieth and Bork's soil trenches documented extensive, deliberate slash and burn agriculture between 1250 and 1500 CE. The charcoal layers are thick. The burned palm stump remnants are pervasive. The Rapanui were clearing forest for agriculture, for firewood, for construction. Humans cleared the present. Rats consumed the future. Both forces operated simultaneously across 3 centuries, and the mathematical result is the same either way. A renewable resource was depleted faster than it could regenerate. Whether the proximate cause was axes or teeth, the structural cause was a harvesting rate that exceeded the regeneration rate. That is the equation. That is always the equation. And the society did not simply collapse in the way Diamond described. In 2016, Hunt, Lipo, and colleagues published an analysis in the journal Antiquity, examining hundreds of the obsidian artifacts called mata that Diamond had described as spear points, evidence of the warfare that supposedly followed deforestation. Their conclusion was damning for the conventional narrative. The vast majority of mata'a showed no evidence of being weapons. They were not pointed. They were not hafted. They were general-purpose cutting and scraping tools, agricultural implements, not instruments of war. The physical evidence for Diamond's post-collapse warfare was at minimum greatly overstated. In 2024, the ancient DNA study, published in Nature by Safa Motesharrei and colleagues, examined the genomes of 15 ancient Rapanui individuals spanning the full pre-contact period. And what they found directly contradicts the catastrophic collapse narrative. There was no pre-contact population bottleneck, no genetic signature of a population crash. The DNA told a story of continuity, not catastrophe. The Rapanui adapted. They did not die en masse before the Europeans arrived. They invented lithic mulch gardens, an agricultural innovation so clever it deserves recognition as one of the great feats of pre-industrial engineering. They broke volcanic rock into small fragments, roughly 2 to 10 centimeters, and spread it across their cultivated plots. The rock mulch retained moisture, moderated soil temperature, and slowly released minerals as it weathered. A 2024 study in Science Advances used satellite imagery to map these rock gardens across the entire island and concluded that the total cultivable area was far less than previously assumed, supporting a peak pre-contact population of roughly 3,000, not Diamond's 15,000. 3,000 people, not 15,000. The Rapanui were not a horde that mindlessly consumed everything in sight. They were a small population that made ingenious adaptations to a degrading environment. They survived. They maintained genetic diversity. They fed themselves. But they still lost the forest. Every single palm, gone. And the adaptations they made, however brilliant, could not restore what had been consumed. The rock gardens kept people alive. They did not bring back the canoes, the seabird colonies, the deep-sea fishing, the topsoil stability, the building materials, or the 70 years of growth locked inside each unborn palm. The Rapanui survived in a diminished world, a world with fewer options, fewer calories, fewer materials, fewer possibilities, a world that could absorb no further shocks. And then the shocks came. Jacob Roggeveen, a Dutch admiral of 62 years, landed on Easter Sunday, April 5th, 1722, with 3 ships and a crew that had been at sea for months. His journal records the encounter with a precision that makes it possible to reconstruct almost hour by hour. He observed standing moai, a treeless landscape, small cultivated plots, and a population he estimated at 2,000 to 3,000. His crew, panicked by the crowd of islanders who swarmed the beach, opened fire with muskets. Between 10 and 12, Rapanui were killed in the first hours of European contact. Roggeveen traded peacefully with the survivors for the remaining week, exchanging cloth and trinkets for poultry and bananas. He then sailed away and did not return. When James Cook arrived in 1774, 52 years later, he found a smaller, malnourished population and toppled moai. The Birdman cult had risen at Oronjo on the rim of the Rano Cow crater, a competitive annual ritual where representatives of the island's clans swam through shark-infested waters to the offshore islet of Motu Nui to retrieve the first sooty tern egg of the season. The clan whose representative returned first ruled for the coming year. The ritual was violent, dangerous, and desperate in a way that suggests a society under extreme stress, reorganizing its power structures around physical competition rather than ancestral authority. The Moai cult, the system of elaborate ancestor veneration that had defined Rapanui society for 5 centuries, was dying or dead. And then came the slavers. In 1862 and 1863, Peruvian ships raided Rapanui and captured between 1,000 and 2,000 islanders, roughly half the remaining population. They were taken to the Chincha Islands off Peru to mine guano. Of those captured, 90% died of disease and brutal working conditions. When international pressure forced the repatriation of survivors, fewer than 100 returned. They brought smallpox back with them. By 1877, The population of Rapanui was 111 people. 111 out of a civilization that had built 900 statues, developed a unique writing system called Rongorongo, navigated 3,700 kilometers of open ocean to reach the most remote inhabited island on Earth, and sustained itself for 5 centuries on a shrinking resource base through sheer ingenuity. The collapse was real, but it was not a single event with a single cause. It was a cascade, and I need you to understand the mechanics of that cascade in detail, because the same mechanics are operating right now at a different scale. First, the loss of the palms degraded the soil. The roots of 16 million palms had held the volcanic topsoil in place on slopes exposed to Pacific winds. Remove the roots, and the rain takes the soil. Erosion indicators in the pollen cores from Rano Raraku spiked sharply during the deforestation period. The rich, loamy soils that had accumulated under centuries of palm leaf fall were replaced by exposed laterite and bare volcanic rock. Agriculture became harder. Each calorie produced required more effort, more land, more innovation. Second, the loss of the palms destroyed the canoe building capacity. Polynesian ocean-going canoes require large, straight timber for the hull. The Jubea palm, while not ideal for all vessel types, was the largest straight wood available on the island. Without it, the Rapanui lost the ability to build deep-water vessels. This meant the end of deep-sea fishing, which had provided a significant portion of dietary protein. Archaeologists have documented the shift in the middens, the refuse piles, over time. Early middens are full of deep-water fish bones, dolphin bones, and pelagic species. Late middens are dominated by nearshore species, shellfish, and rats. The rats that were destroying the forest became, in one of history's bleakest ironies, a staple protein source for the people whose forest the rats had consumed. Third, the loss of the seabird colonies. The palms had provided nesting habitat for large populations of migratory and resident seabirds. Seabirds provide guano, which is natural fertilizer. They also provide eggs and meat. As the forest vanished, the bird populations crashed. The guano supply diminished. The soil grew poorer. The agricultural challenge deepened. Fourth, the freshwater situation degraded. Without tree cover, evaporation from the island's limited freshwater sources increased. The crater lakes at Rano Kau, Rano Raraku, and Rano Eroi, which had been partially shielded by surrounding forest, became more exposed. The Rapanui had never had abundant fresh water. They had no permanent streams. Each degree of deforestation made the water situation incrementally worse. Each of these degradations was individually manageable. The Rapanui were brilliant adapters. The rock gardens, the shift to nearshore fishing and rat consumption, the manavai, walled enclosures that protected crops from wind and salt spray. The tahita, carved basins in rock faces to collect rainwater. Every problem produced an innovation, but every innovation operated within a narrower margin than the last. The system was losing resilience with each generation, like a body that recovers from each illness, but with slightly less capacity each time. And then came the shocks from outside. Roggeveen's musket volley in 1722, venereal disease from subsequent European visitors, the destruction of cultural artifacts by missionaries in the 1830s and 40s, and then the slave raids of 1862 and 63, which removed the last carriers of Rongorongo literacy, the last navigators, the last repository of deep cultural knowledge. By 1877, 111 people remained on an island that had once supported a civilization capable of carving 900 statues, navigating the Pacific, and developing one of the few independent writing systems in human history. Each blow fell on a body less able to absorb it than the last, Not because the Rapanui were weak, because the resource base that provided resilience had already been consumed. That pattern, that specific pattern of compounding, cascading, multi-timescale degradation is exactly what the mathematical models describe. And the models do not care whether the system is 163 square kilometers or 510 million square kilometers. The equations are scale invariant. The dynamics transfer. The math is the same. In 1998, two economists named James Brander and M. Scott Taylor published a paper in the American Economic Review, Volume 88, Number 1, pages 119 through 138. The title was dry in the way that academic papers are dry. The Simple Economics of Easter Island, a Ricardo Malthus model of renewable resource use. The paper was anything but simple. What Brander and Taylor did was take the Lotka-Volterra equations, the predator-prey model that ecologists had been using since the 1920s, to describe the dynamics between, say, wolves and rabbits, and they applied it to humans and their resource base. In the Lotka-Volterra system, the predator population grows when prey is abundant. The growing predator population puts pressure on the prey. The prey population declines, and then, with less food available, the predator population crashes. If the prey regeneration rate is high enough, the prey population recovers, the predator population follows, and the system oscillates. Wolves and rabbits, boom and bust. A cycle that repeats as long as the underlying parameters hold. Brander and Taylor's insight was that this same mathematical structure describes a human population harvesting a renewable resource. The resource, in Easter Island's case the palm forest, grows logistically. It has a maximum stock, K, and a regeneration rate, R. The human population grows when the resource is abundant and contracts when the resource is scarce. The rate at which humans deplete the resource is a function of both the population size and the per capita harvesting rate. Write it out, and you get two coupled differential equations. Resource stock S grows as R times S times the quantity 1 minus S over K, minus the harvesting term, which is a function of labor allocated to harvesting and the abundance of the resource. Population L changes based on whether per capita consumption exceeds or falls below subsistence. When Brander and Taylor calibrated these equations to Easter Island, using a palm regeneration rate, R of approximately 0.04, meaning the forest would take roughly 25 years to recover to half its carrying capacity, if left completely alone, a carrying capacity K of 12,000 resource units, and plausible fertility and mortality parameters drawn from the demographic literature on pre-industrial Polynesian populations. The model produced something that made economists sit up in their chairs. It produced feast and famine cycles, population overshoots, resource collapses, recovery periods, more overshoots, not because anyone in the model was irrational, not because anyone was stupid or greedy or short-sighted. The agents in the Brander-Taylor model are perfectly rational economic actors maximizing their individual utility at every time step. And they still produce collapse. I want to be very precise about why this matters, because it is the part that the popular Easter Island narrative gets catastrophically wrong, and it is the part that matters for understanding our own situation. The collapse does not require stupidity. It does not require ignorance. It does not require malice or incompetence or any moral failing at all. It is an emergent property of the mathematical structure itself. Rational agents harvesting a renewable resource at individually optimal rates will, under a wide range of parameter values, produce collective overshoot and collapse. The tragedy is not that someone made a bad decision. The tragedy is that the math makes the bad outcome the default. Think about what that means. When people tell the Easter Island story as a fable about human foolishness, about the person who cut down the last tree, they are implying that the solution is obvious. Just do not cut the last tree. Just be smarter. Just have more foresight. But the Brandon Taylor model says that is not enough. Even if every individual on the island has perfect information about the state of the forest, even if they all know exactly how many trees are left and exactly how fast they are regenerating, the individually rational decision at each moment is still to harvest. Because if you do not harvest, someone else will. Your restraint does not save the forest. It just means you go hungry while your neighbor eats. The only thing your restraint accomplishes is to make your family worse off while the aggregate depletion rate remains unchanged. This is the tragedy of the commons in its most precise mathematical form. Garrett Hardin described it conceptually in Science in 1968. Brander and Taylor put equations to it 30 years later, and the equations confirmed what Hardin feared. Without binding collective agreements that override individual incentives, the default outcome for a shared renewable resource is depletion. Not because people are bad, because the incentive structure is bad. The math does not need villains. It produces collapse with perfectly virtuous agents. And there is a deeper problem that makes the tragedy worse. A problem that economists have known about for decades and that connects Easter Island to modern civilization with surgical precision. It is called the discount rate problem. How much do you value the future relative to the present? This is not a philosophical question. It is a mathematical one, and the answer you give determines whether a renewable resource survives or dies. If a Jubei palm takes 70 years to reach reproductive maturity, and you are hungry now, what is the rational economic value of preserving that tree? You can use the tree today, right now, to cook tonight's dinner, to build a canoe, to transport a moai that will bring your clan prestige and spiritual power. Or you can leave the tree standing and your great-great-grandchildren might benefit from it in 70 years. If your discount rate is 5% per year, a standard assumption in modern cost-benefit analysis, a resource 70 years in the future is worth approximately 3% of its present value. 3%. The future might as well not exist. And here is where it connects to you. Modern governments routinely use discount rates of 3 to 7% per year when evaluating policy decisions. When the US Office of Management and Budget evaluates whether to invest in a dam, a bridge, an environmental regulation, or a conservation program, it discounts future benefits at rates that make anything more than 30 years away essentially worthless in the calculation. This is not an obscure technical detail. It is the mechanism by which the mathematics of depletion has been built into the policy evaluation frameworks of every major government on Earth. When a cost-benefit analysis concludes that it is not worth preserving a forest because the economic returns from logging exceed the discounted future value of the standing trees, that analysis is performing exactly the same calculation that the Rapanui were performing when they cut palms for firewood. The only difference is that the Rapanui did the calculation intuitively, and we do it with spreadsheets. The outcome is the same. The economist Frank Ramsey, writing in 1928, called temporal discounting of human welfare ethically indefensible, and a practice that arises merely from the weakness of the imagination. He was 25 years old. He died at 26, and his objection has been ignored by the economics profession for almost a century. Elinor Ostrom won the Nobel Prize in Economics in 2009 for showing that Hardin was not entirely right, that small communities can and do develop institutional mechanisms to manage commons sustainably, And the Rapanui may well have been one of her examples. The clan-based territory system, the shared norms around fishing and agriculture, the rock garden innovations, all of these suggest a society that was attempting to govern its commons. But Ostrom's own work acknowledged the conditions under which commons governance fails. When the resource regeneration rate is very low, when the population pressure is very high, when external shocks overwhelm the institutional capacity to adapt. On Easter Island, all three conditions converged. The palms regenerated slowly, the rats devoured the seeds, the humans cleared the adults, and the institutional response, however sophisticated, could not outrun the mathematics. But the Brander-Taylor model has a limitation that matters enormously for understanding the modern parallel. It treats the population as homogeneous. Everyone harvests at the same rate. Everyone consumes at the same rate. Everyone suffers the consequences at the same rate. And that is not how real civilizations work. Real civilizations have hierarchies. Real civilizations have elites who consume more and commoners who consume less. Real civilizations have wealth buffers that allow some people to be shielded from resource scarcity long after others have begun to starve. And that hierarchy, that inequality, changes the mathematics in a way that should keep you awake tonight, because it transforms collapse from a possible outcome into, under certain parameter conditions, an inevitable one. That is what Safa Motesharrei figured out, and that is why NASA did not want its name on the paper. Motesharrei was an Iranian-American applied mathematician, a doctoral candidate in the Department of Mathematics and the School of Public Policy at the University of Maryland. His advisor was Eugenia Calnay, and I need to tell you about Calnay because her credibility is part of this story. Calnay is not a fringe figure. She is a distinguished university professor at UMD, a title reserved for the university's most accomplished scholars. She served as director of the Environmental Modeling Center at NOAA's National Centers for Environmental Prediction. She is the lead author of the NCEP to NCAR reanalysis, a climate dataset so widely used that the paper describing it has been cited over 27,000 times, making it one of the most cited papers in the history of geoscience. She has served on the United Nations Secretary-General's Scientific Advisory Board. When Eugenia Calnay puts her name on a paper, the scientific community pays attention, and she put her name on HANDY. The model is called HANDY, Human and Nature Dynamics, published in Ecological Economics, Volume 101, pages 90 through 102, in 2014. The co-authors were Motesharrei, Jorge Rivas, and Calnay. The model takes the Brander-Taylor framework and adds the one variable that Brander and Taylor left out, inequality. Instead of a single homogeneous population, HANDY splits the population into two classes: commoners, who produce wealth by harvesting nature, and elites, who consume wealth but do not harvest directly. The model has four state variables, each governed by its own differential equation. The equations are deceptively simple. Commoner population X sub C changes at a rate equal to the birth rate beta C times X sub C minus the death rate alpha C times X sub C. Elite population X sub E follows the same structure. Nature Y regenerates logistically, with a regeneration rate gamma of 0.01 per year and a carrying capacity, lambda, of 100 units, minus a depletion term delta times X sub C times Y. And accumulated wealth rose from resource extraction delta times X sub C times Y, and is drained by consumption from both classes. The death rate is where the model gets its teeth. When per capita wealth is above a subsistence threshold, the death rate sits at its minimum value alpha sub m, 0.01 per year. When per capita wealth falls below subsistence, the death rate rises toward its maximum, alpha sub m, 0.07, a seven-fold increase in mortality. And here is the critical mechanism, the one that makes Handy different from every previous collapse model. Elites consume at a rate kappa times the commoner consumption rate, and they have preferential access to accumulated wealth. They do not begin to feel the effects of resource depletion until the wealth buffer is exhausted. Commoners feel it first. Commoners always feel it first. So, in a society with high inequality, high kappa, commoners begin dying from resource scarcity, while elites are still living comfortably. The food is still on the elite table. The lights are still on in the elite houses. The gardens are still tended. The elites see no reason to change course because, from their vantage point, the system is still functioning. The fact that commoner mortality has doubled is, from the elite perspective, regrettable perhaps, but not a systemic crisis. Not yet. Not until the wealth buffer runs out. And by the time it does, nature has been depleted below the regeneration threshold. There is nothing left to save. Motesharrei ran the model across hundreds of parameter combinations and found three distinct regimes that I need you to understand, because the difference between them is the difference between survival and extinction. In the first regime, the sustainable equilibrium, the depletion rate delta is low enough, and the inequality parameter kappa is small enough that population and nature both stabilize at their carrying capacities. The society reaches a steady state and remains there indefinitely. This is the good outcome. It requires both conditions simultaneously, low depletion and low inequality, not one or the other, both. In the second regime, the oscillatory regime, the depletion rate is higher than sustainable but not catastrophically so. The population overshoots, resources decline. The population crashes, resources slowly recover. The population slowly recovers, and the cycle repeats. This is the Brander-Taylor boom and bust. The civilization suffers but survives. It is scarred but not killed. In the third regime, the irreversible collapse, the depletion rate exceeds a critical threshold. For an egalitarian society, that threshold is approximately 5.5 times the sustainable depletion rate. The population overshoots so far and depletes nature so deeply that the resource base cannot recover. The carrying capacity of the environment has been permanently reduced. The civilization collapses and does not come back. And when inequality is high, this threshold drops. With kappa at 100, which is not far from the actual wealth distribution of modern industrial civilization, the system becomes exquisitely sensitive. The margin between oscillatory survival and irreversible collapse narrows to almost nothing. A small increase in delta pushes the system over the edge. The paper states the central finding directly. I spent a long time reading this sentence, and I am going to give it to you exactly as Motesharrei, Rivas, and Kalnay wrote it. The elites, due to their wealth, do not suffer the detrimental effects of the environmental collapse until much later than the commoners. This buffer of wealth allows elites to continue business as usual despite the impending catastrophe. And then, several pages later, the sentence that I believe should have been on the front page of every newspaper in the world. Collapse can be avoided, and population can reach a steady state at maximum carrying capacity if the rate of depletion of nature is reduced to a sustainable level, and if resources are distributed equitably. Both conditions. Not one, both. And when the paper was published and the press started writing about it, When The Guardian ran a headline about a NASA-funded study predicting civilizational collapse, NASA issued a statement within 3 days. NASA did not solicit, direct, or review the study, and the study was not peer-reviewed by NASA. As such, the study does not reflect NASA's position on this topic. The math was never challenged. The equations were never disputed. The agency that paid for the computational tools used to build the model said, "We do not want to be associated with what the tools produced." I want you to hold that fact in your mind for a while. A mathematical model produces a clear, reproducible result. The result says inequality and resource depletion produce collapse. The institution that funded the work does not say the model is wrong. It says the model is not ours. And then the world moves on. The Copenhagen interpretation of civilizational collapse. We refuse to look at what the equations say. We shut the box and pretend the cat is still alive. I want to stay with this institutional dynamic for a moment because it illustrates something that the ultimate hack framework calls the suppression narrative. And it is not the conspiratorial version you might expect. Nobody suppressed the handy paper. It is publicly available. You can download it right now. The equations are right there. What happened was subtler and more effective than suppression. The paper was published, briefly covered by the press, in sensationalized terms that made it easy to dismiss, disavowed by its partial funder, and then forgotten. Not buried, forgotten. The media cycle moved on. The economics profession did not engage with the mathematics. The policy community did not commission follow-up studies. The paper sits in the literature like an unexploded ordnance, technically visible to anyone who looks, functionally invisible to everyone who matters. This pattern is not unique to Handy. It is a pattern that recurs across the entire history of uncomfortable scientific findings. The finding is published. The institution distances itself. The media covers it for a week. Critics attack the framing rather than the mathematics. The public concludes the finding has been debunked, and the actual content of the paper, the equations, the parameter analysis, the reproducible results, sits untouched in a journal that nobody outside the field will ever read. I have seen this pattern before, and I suspect you have too. Not because it is conspiracy, because it is how institutional inertia handles information that threatens the operating assumptions on which the institution depends. The mechanism is not censorship. It is indifference, selectively deployed at precisely the moment when engagement would be most costly, and the cost of engaging with Handy would be enormous. Because the model does not say collapse is caused by bad actors, or corrupt politicians, or greedy corporations. It says collapse is caused by the normal functioning of a stratified society extracting renewable resources. It says the system that produces the collapse is the system itself, and that means the solution cannot be a reform or an adjustment or a new technology. The solution requires changing the structure of the system, specifically the depletion rate and the inequality ratio, in ways that would reduce elite consumption and redistribute wealth downward. That is not a message that any institution funded by elite wealth is eager to amplify. But maybe the model is too simple. Maybe 4 equations cannot capture the complexity of real civilizations. That is a reasonable objection, and it deserves serious answers. So let me give you 3 independent ones, from 3 different disciplines, using 3 different methodologies, all of which arrive at the same conclusion. Joseph Tainter is an anthropologist at Utah State University who published The Collapse of Complex Societies in 1988 through Cambridge University Press. His framework is entirely different from Motesharrei's. Tainter is not writing differential equations. He is looking at the historical record across a dozen collapsed civilizations the Western Roman Empire, the Maya, the Chaco Canyon Anasazi, the Hittites, the Mycenaean Greeks, and asking a different question. Not why did they collapse? Why did they not prevent the collapse, given that the problems were visible for decades or centuries before the end? Tainter's answer is one of the most quietly devastating ideas in all of social science. He argues that civilizations solve problems by increasing complexity. When a society faces a challenge, whether resource scarcity, external threats, internal conflict, or administrative overload, it responds by adding layers of bureaucracy, infrastructure, specialization, and coordination. And for a while this works brilliantly. The first irrigation canal transforms a desert into farmland. The first standing army repels the invaders. The first bureaucracy collects taxes efficiently. Each increment of complexity solves a real problem and produces a real return. But each subsequent increment costs more than the last and delivers less. The 10th irrigation canal produces marginally more food at significantly higher administrative cost. The third layer of bureaucracy produces marginally better coordination at significantly higher fiscal burden. Eventually, the marginal returns on additional complexity approach zero and then turn negative. The society is spending more to maintain its existing complexity than the complexity is delivering in benefits. And the only solution the society knows, the only tool in its institutional toolkit, is to add more complexity, which makes the problem worse. Tainter does not say societies collapse because their leaders are incompetent. He says they collapse because the strategy that built them, increasing complexity to solve problems, inevitably reaches a point of diminishing returns, where, in his words, collapse becomes an economizing process, a rational shedding of costs that the system can no longer sustain. The Western Roman Empire did not fall because barbarians were strong. It fell because maintaining the legions, the roads, the aqueducts, the bureaucracy, the currency, and the imperial administration had become more expensive than the empire could fund. By the 4th century, the Roman army consumed between 50 and 70% of the imperial budget. Taxation was crushing productive capacity. The Diocletian reforms of the late 3rd century attempted to solve the fiscal crisis by adding yet more bureaucracy, more taxation districts, more price controls, more regulatory complexity. Each reform solved a short-term problem and deepened the long-term one. Citizens in frontier provinces were defecting to the barbarians because life under the empire, with its crushing tax burden and forced labor obligations, had become more burdensome than life outside it. The barbarians were not conquering a strong empire. They were inheriting the shell of an exhausted one. The structural cause was that Rome had exceeded the point of diminishing returns on complexity decades before the barbarians arrived at the gates. The fall was not a catastrophe. It was a release. I want to be clear about why I am telling you about Rome. It is not because Rome fell, and therefore we will fall. That reasoning is superficial and unhelpful. It is because the mechanism Tainter identifies, the diminishing returns on complexity, operates independently of the specific civilization. It is a mathematical property of how complex systems interact with the problems they are designed to solve. And it is operating right now. The cost of maintaining the complexity of modern global civilization, its financial systems, its supply chains, its regulatory frameworks, its military structures, its healthcare systems, its information infrastructure, is growing faster than the returns that complexity delivers. Every new regulation imposes compliance costs. Every new technology requires new infrastructure. Every new international agreement requires new enforcement mechanisms. The marginal costs of running a civilization this complex are rising, and the marginal benefits are in many domains declining. Now consider a second framework. From a completely different direction. Peter Turchin is a complexity scientist, originally trained as a population ecologist, who founded a discipline he calls Cliodynamics, the mathematical modeling of historical dynamics. Turchin earned his doctorate studying bark beetles. He spent years modeling predator-prey dynamics in forest ecosystems. And then he turned to human history and realized the same Lotka-Volterra structure, the same predator-prey oscillations, appeared in the historical record of empires and civilizations, repeating on 2 to 3 century cycles. In 2010, Turchin published a commentary in Nature, volume 463, page 608, in which he made a specific, quantitative, falsifiable prediction. I am going to quote it directly. The next decade is likely to be a period of growing instability in the United States and Western Europe. He specified the peak near 2020. He identified the primary drivers as population pressure on wages, elite overproduction, state fiscal stress, and political polarization. He defined elite overproduction precisely. It is the condition where a society produces more people who aspire to elite positions, advanced degrees, political offices, executive roles, than there are elite positions available. The surplus elites become destabilizing. They fund populist movements. They polarize the political system. They compete with each other with increasing desperation, and the institutional fabric of the society tears under the strain. He published this in 2010. He predicted instability peaking around 2020, and then 2020 happened. I am not going to tell you that Turchin predicted a specific pandemic or a specific insurrection. He did not. What he predicted was a structural window of maximum instability, and the prediction was derived not from intuition or punditry, but from quantitative analysis of demographic and economic variables across 2 millennia of recorded history. The model produced a date, and the date was right. In 2023, Turchin published a book called End Times, in which he laid out the full analysis. The data is meticulous. Real wages in the United States peaked in 1973 and have been stagnant or declining in real terms since. The number of Americans with advanced degrees has roughly tripled since 1970, while the number of elite positions, congressional seats, Fortune 500 CEO roles, tenured professorships, federal judgeships, has remained approximately constant. The ratio of aspirants to positions has been climbing for 50 years. Each surplus elite becomes a potential factional leader, a funder of populist movements, a destabilizing agent in a system that cannot accommodate them. Look at this from the handy perspective, and the pattern becomes clearer. Turchin's elite overproduction is a specific mechanism within the broader handy dynamic. When kappa is high, when elites consume disproportionately, and when the number of elites grows faster than the resource base can support, the system enters a crisis that is simultaneously ecological, economic, and political. The resource depletion drives the scarcity. The scarcity hits the commoners first. The elites, buffered by wealth, continue to compete for status through increasingly destructive means. The political system fragments. The institutional capacity to respond to the ecological crisis is destroyed by the political crisis, and the ecological crisis deepens because nobody is left with the authority or the incentive to address it. On Rapanui, the parallel is almost too precise to be comfortable. As the resource base degraded, the Moai building clan chiefs, the elite class, competed with each other by building larger and larger statues. The status competition consumed resources that could have been invested in adaptation. The Matatoa, The warrior class emerged. The birdman cult replaced the ancestral authority. Institutional continuity broke down at precisely the moment when institutional continuity was most needed. The same pattern Turchin identifies in the late Roman Republic, in pre-revolutionary France, in the Weimar Republic. The same pattern he sees emerging in the 21st century United States. 3 frameworks: predator-prey resource dynamics, diminishing returns on complexity, secular cycles, and elite overproduction, plus a systems dynamics model validated against half a century of data. In 1972, a team at MIT, led by Donella Meadows, Dennis Meadows, and Jorgen Randers, published The Limits to Growth, commissioned by the Club of Rome. They built a computer model called World 3, with 5 interacting sectors: population, industrial output, food production, natural resources, and pollution. They ran 12 scenarios. The standard run, assuming no major changes in policy or technology, projected that industrial output, food per capita, and population would peak in the first half of the 21st century and then decline sharply. Not gradually, sharply. A cliff followed by a long slide. Donella Meadows was 31 years old when the book was published. She was a biophysicist by training, a systems thinker by disposition, and a better writer than most scientists ever learned to be. The Limits to Growth was written with a clarity that made it accessible to non-specialists, which is part of what made the backlash so fierce. The book sold 30 million copies and was translated into 37 languages. It became one of the most influential and most attacked scientific publications of the 20th century. The attacks came primarily from economists, and they were relentless. William Nordhaus, who would later win the Nobel Prize in Economics for his work on climate, published a critique in 1973, arguing that the model's treatment of resource substitution was naive. Julian Simon, perhaps the most vocal critic, built an entire career arguing that human ingenuity would always find substitutes for any depleting resource, and that the very concept of physical limits to growth was an illusion. In 1980, Simon famously bet Paul Ehrlich that the price of 5 commodity metals would fall over the next decade. He won the bet. The prices did fall, and for many people, that settled it. Limits to growth was wrong. Markets work. Technology saves. End of story. But the bet was about prices, not about physical quantities. And prices are human constructs, influenced by subsidies, currency manipulation, labor conditions, and market speculation. They are measures of short-term economic scarcity, not long-term ecological sustainability. The fact that copper was cheaper in 1990 than in 1980 told you nothing about the long-term trajectory of resource depletion, soil loss, fisheries decline, or atmospheric carbon accumulation. Simon won the bet and lost the argument, but it took decades for the data to prove it. Donella Meadows died in 2001 at the age of 59 from bacterial meningitis before she could see the vindication of her work. But the data kept accumulating. In 2008, Graham Turner at Australia's CSIRO compared 36 years of actual observed data to the limits to growth projections. The observed data tracked the standard run with disturbing accuracy. Population, industrial output, food production, pollution, all within the projected corridors. In 2021, Gaia Harrington, then at the global consulting firm KPMG, updated Turner's analysis using data through 2020 and published it in the Journal of Industrial Ecology, Volume 25, pages 614 through 626. Her conclusion, and I am going to give you her exact words because they matter. BAU2 and CT scenarios show a halt in growth within a decade or so from now. Both scenarios thus indicate that continuing business as usual, that is, pursuing continuous growth, is not possible. That is a researcher at KPMG, one of the largest professional services firms on Earth, publishing a peer-reviewed paper that says the economy as currently structured cannot continue to grow past approximately the 2030s. She is not an activist. She is not an environmentalist. She is an analyst at a major consulting firm who compared a 50-year-old model to 50 years of data and found that the model was right. The economists who spent decades ridiculing the limits to growth have not, as far as I can find, issued corrections or retractions. The ridicule is still in the textbooks, the data is in the journals, and the public was left with the impression, for 50 years, that the limits to growth had been debunked, when in fact it had been validated. 3 frameworks: predator-prey resource dynamics, diminishing returns on complexity, secular cycles and elite overproduction, plus a systems dynamics model that has been validated against 50 years of data. They use different equations, different variables, different data sets, and different disciplinary traditions, and they all converge on the same structural conclusion. The default trajectory of complex civilizations operating under current parameters is overshoot and decline. Sustainability is the special case. Collapse is the general case. And the transition from one to the other happens not with a visible event, but with a long, slow, invisible crossing of a threshold that the system was not designed to detect, because the people who would need to detect it are protected from the need to look. That is the ghost forest. The adult trees still standing, the canopy still green, the seeds already eaten, and nobody looking down. Now let me show you the modern numbers, not metaphors, arithmetic. Earth Overshoot Day is the date each year when humanity's demand on nature exceeds what Earth's ecosystems can renew in that year. In 2025, it fell on July 24th. By late July, we had consumed a full year of renewable biological resources. Everything from August through December is deficit spending against the planet's ecological capital. Humanity currently uses approximately 1.8 Earths of biocapacity per year. The trend is not stable. In 1970, Earth Overshoot Day was December 29th. We were roughly in balance. By 2000, it had moved to September 23rd. By 2020, August 22nd. By 2025, July 24th. The date moves earlier. The deficit widens. On Easter Island, the palm forest had a regeneration rate, R, of approximately 0.04. The Rapanui were harvesting it at a rate that Brander and Taylor estimated at 3 to 5 times sustainable levels. We are currently depleting global biocapacity at 1.8 times the sustainable rate. The ratio is lower, but the system is larger, the feedbacks are slower, and the depletion is accelerating. Forests. The 2025 Forest Declaration Assessment found that 8.1 million hectares of forest were lost globally in 2024. Of that, 6.73 million hectares were tropical primary rainforest, the kind that contains the highest biodiversity, stores the most carbon, and takes centuries to regenerate if it regenerates at all. That rate is 63% higher than the trajectory needed to halt deforestation by 2030. The target 145 countries pledged to meet at COP26. For the first time in the modern record, fire, rather than agricultural clearing, was the leading driver of tropical forest loss. The system is beginning to consume itself. Forests burning release carbon. Carbon warms the atmosphere. Warmer atmospheres produce more fires. The feedback loop is closing. And once a tropical forest burns, the soil beneath it, exposed to direct equatorial sun, can bake into a laterite hardpan that nothing will grow in for decades. The fire does not just kill the trees, it kills the possibility of trees. Topsoil. The FAO's 2014 assessment warned that the world's topsoil could be gone within 60 years at current degradation rates. In 2022, the FAO updated to say 90% of global topsoil could be at risk by 2050. Now, I want to be honest about these numbers, because this channel does not deal in exaggeration. Hannah Ritchie at Our World in Data has pointed out that the 60 years figure is a global average masking enormous regional variation. Some soils are actually thickening. 16% of soils worldwide have lifespans under 100 years, which is alarming, but many others are stable. The alarm is real, but unevenly distributed. What is not debatable is the directional trend. We lose 24 billion tons of fertile soil per year globally. It takes roughly 500 years to generate 1 inch of topsoil through natural processes. We are mining a resource that regenerates on geological timescales and depleting it on agricultural timescales. In the Handy model, that is a regeneration rate gamma so low relative to the depletion rate delta that the system is deep in the irreversible collapse regime. Water. The Ogallala Aquifer spans 8 states beneath the American Great Plains. It irrigates roughly 30% of all U.S. cropland. The water accumulated over millions of years during the Pleistocene. We have been pumping it for less than 80 years, and in the southern high plains of Texas and Kansas, the water table has dropped 100 to 200 feet. Scientific American reports that the Ogallala is being depleted at the equivalent of 18 Colorado rivers per year. The recharge rate in parts of Texas is less than 1 millimeter per year. Do the math. Depletion at meters per year, recharge at fractions of a millimeter. The water is not coming back, not in any time frame that matters for the farmers whose livelihoods depend on it, not for the cities whose food supply depends on those farmers, not for you. And this is where the title of this script becomes literal. The decision that killed Easter Island is being made right now. It is being made in the Texas Panhandle, where farmers know the Ogallala is depleting and continue to pump because their mortgage payments are due this month, and the water is still there today. It is being made in the Amazon, where cattle ranchers clear primary forest because the profit from beef exceeds the fine for illegal deforestation, if any fine is levied at all. It is being made in the South China Sea, where fishing fleets deploy sonar and GPS-guided purse seines to harvest fish stocks that are already below sustainable levels, because the boats are already built, the crews already hired, the loans already taken out. It is being made in every Ministry of Finance that evaluates infrastructure projects at a 5% discount rate, mathematically guaranteeing that the present always outweighs the future. These are not evil decisions. They are not stupid decisions. They are exactly the decisions that the Branded Taylor model predicts rational agents will make. They are the decisions that the math says they must make, given the incentive structure, given the discount rate, given the absence of binding collective agreements that override individual rationality. Every one of these decisions is the last tree, not one moment, 10,000 moments. Every day, all over the planet. But there is a counterexample that matters, and I am going to give it to you, because intellectual honesty is more important than narrative convenience. The North China Plain Aquifer was depleting at roughly 1 meter per year for 2 decades, creating a cone of depression spanning 50,000 square kilometers. A 2025 paper in Nature Communications documented that since 2020, The water table has been recovering at about 0.7 meters per year. The cause is the South to North Water Diversion Project, one of the largest infrastructure projects in human history, combined with enforced pumping restrictions. Deliberate, costly, politically difficult intervention reversed the depletion curve. It can be done. Policy can change the parameters. The Handy model's depletion rate delta is not destiny. It is a variable. But changing it required the Chinese government to mobilize resources on a scale comparable to a wartime economy, to build a canal system spanning 1,400 kilometers, and to impose restrictions that affected millions of farmers. No democratic government has yet matched this for its own aquifers. The question is not whether it is possible. The question is whether the political systems we have built are capable of doing it at the speed the math requires. Fisheries. The FAO's 2025 assessment found that 35.5% of assessed global marine fish stocks are overfished. More than 1 in 3 fish populations harvested faster than it reproduces. In the Mediterranean and Black Sea, 52% of stocks are overfished, which is actually an improvement from 87% a decade ago, thanks to aggressive management. The Mediterranean proves recovery is possible. It also proves that even after a decade of the most intensive fisheries management in the world, more than half the stocks are still in decline. Recovery is possible, slow, expensive, and currently losing the race against depletion at the global level. And then there is the atmosphere. I have deliberately saved this for last, because it is the one resource system where the numbers are most precisely known and most relentlessly tracked. The atmospheric carbon budget is the total amount of carbon dioxide that can be emitted while keeping global warming below a given threshold. The IPCC's 6th assessment report, published in 2021, estimated that to have a 50% chance of keeping warming below 1.5 degrees Celsius, the remaining carbon budget from 2020 was approximately 500 gigatons of CO2. At current emission rates of roughly 40 gigatons per year, that budget will be exhausted by approximately 2032. 6 years from now, the budget for a 2-degree target is larger, roughly 1,100 gigatons, but at current rates, it is exhausted by the mid-2040s. This is the Brander-Taylor dynamic applied to the atmosphere. The atmospheric carbon sink has a carrying capacity, the level of CO2 concentration, that does not produce catastrophic warming. It has a regeneration rate, the rate at which natural carbon sinks, forests, oceans, soils, absorb CO2 from the atmosphere. And it has a depletion rate, the rate at which human emissions add CO2 faster than the sinks can absorb it. The depletion rate currently exceeds the regeneration rate by roughly half. We add 40 gigatons per year. The sinks absorb about 20. The difference accumulates. The concentration rises. And unlike an aquifer or a fishery, where the depletion is regional and can in theory be compensated by conservation elsewhere, the atmosphere is a single global commons. Every ton of CO2 emitted anywhere affects the climate everywhere. There is no North China Plain solution for the atmosphere. There is no regional management plan. There is only the global total. And the global total is not declining. It is still rising. After decades of warnings, after the Kyoto Protocol and the Paris Agreement and 28 annual conferences of the parties, global CO2 emissions reached a record high in 2023. A record. Not a plateau, not a decline, a record. The institutions built to change the trajectory have, so far, failed to change the trajectory. The adult trees are still standing. The conference declarations are still being issued, and the concentration keeps rising parts per million by parts per million, year after year. Take all of these numbers together: the overshoot ratio, the deforestation acceleration, the topsoil mining, the aquifer drawdown, the fisheries decline, the carbon budget countdown. In the language of the handy model, they all represent the parameter delta, the per capita rate at which nature is being consumed. And every single one of these measurements, without exception, places delta above the sustainable threshold in Motesharrei's equations. Some of them well above. Now recall the second parameter, kappa, inequality. The Oxfam report for 2024 found that the richest 1% of humanity owns more wealth than the bottom 95% combined. In the handy model, kappa values of this magnitude produce a specific dynamic that is the most important thing I will say in this entire script. The elite consumption buffer grows so large that elites do not perceive the crisis until long after the commoners have begun to suffer. By the time elite consumption begins to fall, nature has been depleted past the recovery threshold. The feedback loop that would allow the system to self-correct has been broken by the very wealth that was supposed to provide security. I need to say that again because I want the mechanical precision to be clear. Inequality is not just morally problematic. It is dynamically destabilizing. It breaks the feedback loop between depletion and response. In a system with low inequality, everyone feels scarcity at roughly the same time, which means political pressure to change course builds early, when there is still time to act. In a system with high inequality, the people with the power to change course are the last people to feel the scarcity, and by the time they feel it, the window has closed. The parameters cannot be adjusted because the resource base has already crossed the threshold below which adjustment matters. The elite buffer is not a failure of the system. It is the mechanism by which the system produces collapse, and the people who benefit from the buffer are the same people who would need to dismantle it. I keep coming back to the moai. The statues grew larger over time. The earliest moai were 2 to 4 meters tall. The largest one, transported and erected on a platform, was roughly 10 meters and 75 metric tons. And the largest one ever attempted, El Gigante, still lying half-carved in the quarry at Rapa, was 21.6 meters tall and would have weighed approximately 270 tons. It was never finished. It was never moved. It lies there still, a monument to ambition that exceeded every physical constraint of the island. The quarry itself tells a story that I find difficult to look away from. Rapa is a volcanic, tough cone on the eastern slope of the island, and it served as the primary quarry for moai production for roughly 500 years. Inside and around the crater, approximately 397 moai lie in various states of completion. Some are barely begun, just outlines carved into the rock face. Some are nearly finished, but never detached from the bedrock. Some are fully carved, detached, and moved partway down the slope before being abandoned. They lean against the quarry walls, like passengers waiting for a bus that never came. The unfinished moai are not evidence of sudden catastrophe. They are evidence of a project that gradually became impossible to sustain. The labor was there, the skill was there, the desire was clearly there, because they kept attempting bigger ones even as conditions deteriorated. What was not there, increasingly, was the caloric surplus to feed the workers, the social organization to coordinate the effort, and ultimately, the motivation to continue once the ancestral authority system that justified the effort had been undermined by ecological stress. The quarry did not stop production because someone gave an order. It stopped because the civilization that had created the demand could no longer generate the supply. The last sculptor put down his basalt pick and walked away, and no one picked it up again. Consider what the moai represented. Each statue was a portrait of a specific ancestor, erected on a clan's Ahu platform to channel the ancestors' spiritual power, their mana, to protect the living community. The moai were not decorative. They were functional in the deepest sense the Rapanui understood. They were infrastructure for spiritual protection, for agricultural fertility, for social order. To stop building them was not an economic decision. It was a declaration that the ancestors could no longer protect you, that the spiritual economy had failed. Tainter would recognize this instantly. The complexity ratchet. Each generation inherits the previous generation's infrastructure and adds to it. Each addition costs more. Each addition produces less marginal return. But no generation voluntarily simplifies. No generation looks at the monuments and says we cannot afford this anymore. Because the monuments are not just engineering. They are our identity. They are legitimacy. They are the proof that the civilization is worthy of its own existence. To stop building is not an economic decision. It is an existential one. It says the story we told ourselves about who we are is over. Global GDP must grow. That is the modern moai. The assumption is not merely economic. It is existential. Every government, every central bank, every international development institution, every pension fund, every retirement account operates on the premise that the economy must expand continuously, indefinitely, compounding at 2 to 3% per year on a planet with finite resources and finite waste absorption capacity. A 2% annual growth rate means the economy doubles every 35 years. 3% and it doubles every 23 years. Run that forward a century, and you need an economy 4 to 8 times larger than today's, extracting 4 to 8 times as much from a resource base that is already operating at a deficit of 1.8 Earths per year. To question that premise is not merely to propose an alternative economic model. It is to challenge the foundational narrative of industrial civilization. The moai was the physical proof that the ancestors watched over you. GDP growth is the numerical proof that the system works, that progress is real, that your retirement account will be worth more in 30 years than it is today. To say growth cannot continue is to say the story is over, and nobody in power will say it, not because they do not understand the math, because saying it crashes markets, because saying it ends careers, because saying it undermines the legitimacy of every institution that depends on the growth assumption for its continued existence. The clan chiefs kept ordering bigger moai even as the forest shrank around them. The finance ministers keep targeting higher GDP even as the biocapacity deficit widens beneath them. The mechanism is the same. The game theory of the last tree applies here too. On Easter Island, the decision to cut or not cut was not made by one person at one moment. It was the cumulative result of thousands of individual decisions over 3 centuries, each rational in isolation, each contributing to a collective outcome that no individual chose. No Rapanui woke up and said, "Today I will destroy the future." They woke up and said, "I need firewood. I need to clear this plot for sweet potatoes. I need a canoe to fish for my children." The forest did not end with a dramatic final act. It ended with 10,000 ordinary Tuesdays. The game theory is straightforward and devastating. In a common pool resource, without binding collective agreements, defection dominates cooperation. If you restrain your harvesting but others do not, you bear the cost and receive none of the benefit. The only rational strategy is to harvest what you can before it is gone, not because you want to destroy the resource, because you know that if you do not take it, someone else will. And the discount rate makes it worse. A 5% discount rate, standard in policy analysis, means a resource 70 years in the future is worth approximately 3% of its present value. We have institutionalized the mathematics of depletion in the spreadsheets we use to make decisions. The equations that produce collapse are not hidden in obscure academic papers. They are built into the cost-benefit frameworks that every government uses to evaluate every policy. Every dam, every pipeline, every forest concession, every fisheries quota is evaluated with a discount rate that mathematically guarantees that the present always outweighs the future. The math is not metaphorical. The differential equations governing Easter Island's collapse and the differential equations governing modern resource depletion have the same structure, the same predator-prey dynamics, the same phase portraits, the same bifurcation thresholds. The variables have different names: population of Rapanui versus population of Earth, palm regeneration versus biocapacity regeneration, kappa measured in Moai height versus kappa measured in wealth, Gini coefficients. But the mathematical structure, the thing that determines whether the curves level off or crash, is identical, not similar, not analogous, identical. In 1995, Jared Diamond wrote an essay called Easter's End for Discover magazine. He posed the question that has haunted every discussion since. What did the Easter Islander who cut down the last palm tree say while he was doing it? It is a powerful image, a single person, a single tree, a single moment of irreversible choice, but it is the wrong image. The last tree was not cut down by one person in one moment of catastrophic foolishness. It was the culmination of 3 centuries of compounding forces: rats eating seeds, humans clearing forest, soil eroding, regeneration capacity collapsing invisibly beneath a canopy that still looked green. The person who cut the last tree probably did not know it was the last tree. The forest had been thinning for generations. Each generation inherited a slightly diminished world and treated it as normal. The children born into a world with fewer trees did not miss the trees they had never seen. The ecologist Daniel Pauly coined the term shifting baseline syndrome in 1995. The same year, Diamond published his Easter's End essay. Pauly was writing about fisheries, about how each generation of fisheries scientists accepts the fish stock levels they first observed as the baseline against which decline is measured. A marine biologist who began their career in 1980 would treat 1980 stock levels as normal and measure decline from there. But a biologist from 1950 would know that the 1980 stocks were already severely depleted relative to 1950. And a biologist from 1920 would know that the 1950 stocks were already a fraction of what existed before industrial fishing began. Each generation's normal is the previous generation's catastrophe. This is not a metaphor. It is a measurement bias that has been documented across dozens of ecological systems, and it operates in exactly the same way in human societies. Your grandparents remember forests, rivers, bird populations, and fish catches that you have never seen. Your great-grandparents remember an abundance that your grandparents would find astonishing. And your children will grow up treating today's depleted world as normal, as the baseline from which they measure whatever further depletion occurs during their lifetimes. You have never seen the Ogallala at full capacity. The aquifer was already being pumped when the first measurements were taken. You have never seen the Grand Banks teeming with cod the way they were in the 1600s, when the explorer John Cabot reported that the sea was so thick with fish that you could almost walk across them. The Grand Banks cod fishery was one of the great renewable protein sources in human history. It fed Europe for 5 centuries. In 1992, the Canadian government declared a moratorium on cod fishing because the stock had collapsed to 1% of its historical biomass. 1%. 35,000 fishermen lost their jobs overnight. The moratorium was supposed to be temporary, 2 years, maybe 3. It has now lasted 34 years. The cod have not come back. The ecosystem shifted to a new state dominated by crab and shrimp. And the original configuration, the one that sustained a fishing industry for 500 years, may never return. That is what crossing an irreversibility threshold looks like in practice. Not a gradual decline with a gradual recovery. A permanent shift to a poorer state. You have never walked through the temperate forests that once covered most of the eastern United States, before European settlers cleared 90% of them for agriculture. You have never breathed air with 280 parts per million of carbon dioxide, which was the atmospheric concentration for the entirety of human civilization, until about 1950. As of 2025, it is over 425 parts per million. Your baseline has already shifted. The world you experience as normal, as the way things are, is already the diminished version. And every decision you make, every consumption pattern you accept, every economic growth rate you expect, is calibrated to a world that is already past the point a Rapanui from 1200 CE would recognize as sustainable. This is not a personal failing. This is a structural feature of how human cognition interacts with slow-moving ecological change. If a forest loses 1% of its canopy per year, no single year produces a visible change. The forest looks the same this year as it did last year. It is only when you compare a photograph from 50 years ago to a photograph from today that the loss becomes visible. But nobody lives in 50-year time lapses. We live in days and weeks and seasons, and on those timescales, the world appears stable. The Rapanui who cleared a plot of forest in 1300 saw a forest around them that looked largely intact. The fact that the forest was 30% smaller than it had been a century earlier was not visible to them because they had never seen the forest a century earlier. Their baseline was the diminished forest. They were born into it. They accepted it. They thought it was the world. We are doing the same thing right now, and the data proves it. In 2019, a study in Science by researchers at Cornell found that North America had lost roughly 3 billion birds since 1970. 3 billion, nearly 1 in 3. The skies are emptier than they were 50 years ago, and nobody notices because nobody remembers what the skies used to look like. Your grandmother might remember, your children will not. Their baseline will be your depleted sky. The Ogallala is a ghost aquifer. The water is still there. The pumps are still running. The crops are still growing. But the recharge rate in parts of Texas is less than 1 millimeter per year. The water being pumped fell as rain during the Pleistocene 10,000 years ago. It is Pleistocene water growing Holocene crops to feed Anthropocene consumers, and the balance sheet does not close. The pumps will run until they cannot. And when they stop, the agriculture that feeds 30% of American cropland stops with them. Global topsoil is a ghost soil. The farms are still producing record yields, propped up by synthetic fertilizers that mask the underlying depletion of organic matter. The fertilizers keep the canopy green. Underneath, the microbial communities, the mycorrhizal networks, the earthworm populations, the fungal webs that give soil its structure and its fertility, are declining. The soil still produces, but it is producing on borrowed time, maintained by inputs that are themselves derived from fossil fuels that are themselves finite. The fisheries are a ghost ocean. The catch comes in, the markets are full, but 35.5% of the stocks being fished are reproducing slower than they are being harvested. The boats sail, the nets fill, and the spawning biomass declines year after year, stock after stock. The air still feels breathable. The weather still changes with the seasons, but 425 parts per million of CO2 is already higher than at any point in the last 800,000 years of ice core record. The remaining carbon budget for 1.5 degrees of warming will be exhausted within this decade at current emission rates. The sky still looks blue. The numbers underneath it tell a different story. And perhaps the most unsettling ghost of all is the one we carry in our own perception. The ghost baseline. The world you were born into felt complete. It felt like the world. You did not experience it as degraded because you had nothing to compare it to. But the world you were born into had already lost 90% of its large ocean fish compared to pre-industrial levels. It had already lost roughly 3 trillion trees, about half the trees that existed before the rise of agriculture. It had already lost 83% of wild mammal biomass. The world you call normal is a remnant. You are living in the ghost of an ecosystem, calling it home, calibrating your expectations to its diminished capacity, and treating any further loss as the deviation from an already devastated baseline. The same equations, the same dynamics, the same lag between invisible depletion and visible consequence, the same elite buffer insulating the decision makers from the feedback that would force them to act, the same rational individual choices producing collective catastrophe, the same ghost. Motesharrei's equations do not have a variable for intention. They do not have a variable for wisdom, for foresight, for moral character. They have population, resources, wealth, and inequality. The outcome depends on the parameters, not the personalities. And the parameters, the actual measured values as of today, place this civilization in the regime that the model identifies as trending toward irreversible type N collapse. The model also shows clearly, reproducibly, and without ambiguity that the sustainable equilibrium exists. It is reachable, but reaching it requires reducing delta and reducing kappa simultaneously before nature crosses the recovery threshold. The North China Plain aquifer proves delta can be reduced by policy. The Mediterranean fisheries prove management can reverse depletion. It is not physically impossible. The question the math cannot answer is whether a species that has built its entire identity around growth, that has elevated the growth assumption to the status of religious doctrine, that has structured its political systems to serve elite interests and insulate elite consumption from ecological feedback, will choose, voluntarily, deliberately, and at sufficient speed to change the parameters that determine whether the curves level off or crash. I want to make this concrete because abstract warnings are easy to dismiss. Right now, in 2026, the United States Congress is debating Farm Bill reauthorization. Embedded in that legislation are crop insurance subsidies that incentivize farmers in western Kansas to continue irrigating with Ogallala water even as the aquifer drops below pump reach. The subsidy structure makes it economically rational for individual farmers to deplete the aquifer because the federal government absorbs the downside risk. This is the tragedy of the commons, with a government subsidy attached. It is not an accident, it is policy. And the policy is the mathematical equivalent of handing sharper axes to the Easter Islanders. Right now, the European Union's Common Fisheries Policy sets total allowable catches that member states consistently exceed. The enforcement mechanisms are weak. The political pressure to maintain fishing employment in coastal communities overrides the scientific advice on sustainable yields. The economists who set the catches use discount rates that prioritize present economic output over future stock recovery. The same discount rate problem, the same mathematics, the same result. Right now, Brazil's National Institute for Space Research, INPE, reports deforestation in the Amazon using satellite data. When the data shows acceleration, as it did in 2024, political pressure is applied to the institute, to the methodology, to the definition of what counts as deforestation, not to the deforestation itself. The measurement is challenged. The phenomenon continues. This is the institutional version of the elite buffer. The data exists. The people in power do not want to see it. And so they do not look at the measurement. They look at the measurer. This is not a story about Easter Island. Easter Island is a lab result, a proof of concept, a closed system demonstration of what happens when the parameters exceed certain values. It is a 163 square kilometer petri dish that produced under controlled conditions the exact dynamics that 4 independent mathematical frameworks predict for planetary scale civilizations operating under the parameters we are currently operating under. The story is about the parameters, and the parameters are not historical. They are current. They are being set right now. In budget negotiations and trade agreements and subsidy structures and discount rate assumptions, by people who will not feel the consequences within their lifetimes, which is exactly the dynamic that makes the handy model produce collapse. I need to tell you something personal here because I promised at the beginning that this channel is honest about uncertainty, and I want to honor that. I do not know where the irreversibility threshold is. Nobody does. The handy model can tell you that it exists. It can tell you what parameter combinations produce it. It can tell you that once you cross it, recovery becomes impossible. But it cannot tell you with precision whether we have already crossed it or whether we are 10 years away or 30 years away. The Earth system is more complex than 4 differential equations. The feedbacks are non-linear. The tipping points interact with each other in ways that are still being mapped. We know that the Amazon rainforest has a dieback threshold, a point at which the forest can no longer generate enough of its own rainfall to sustain itself and begins an irreversible transition to savanna. We know the threshold exists. We do not know exactly where it is. We know we are closer to it than we were 20 years ago. We do not know if we have crossed it. This uncertainty is not a reason for comfort. It is a reason for terror. Because in any system with an irreversibility threshold, the rational strategy is to maintain a large safety margin. You do not drive toward a cliff at high speed and comfort yourself with the thought that you do not know exactly where the edge is. You slow down. You stop. You change direction. The uncertainty about the precise location of the threshold makes early action more important, not less. And instead, the uncertainty has been weaponized as a reason for delay. We do not know exactly how bad it will be. We do not know the precise timeline. Therefore, we can wait. Therefore, we need more research. Therefore, we should not act precipitously. This is the elite buffer operating in real time. The people making these arguments are the people who will feel the consequences last. Their children will attend schools with functioning air conditioning. Their homes are not in the floodplains. Their portfolios are hedged against climate risk. They can afford to wait. And so they counsel patience. And the parameters do not change. The Rapanui who built the last moai did not know they were building the last one. They did not know that the caloric surplus required to feed the work crew would soon fall below the minimum. They did not know that the institutional framework that justified the construction would collapse within a generation. They experienced uncertainty, and in the face of uncertainty, they did what they had always done. They kept building, because building was the identity, because stopping was unthinkable, because the alternative was to admit that the story was over. The Rapanui did not make that choice. They adapted brilliantly within the constraints of their situation. They invented rock gardens and survived. But they never reversed the depletion. The forest never came back. The canoes were never rebuilt. The deep-sea fish were never caught again. They survived, diminished, in a world they had permanently reduced. And then the ships arrived, and the cascade finished what the mathematics had started. The model is running right now. The parameters are set. Delta is above threshold. Kappa is in the elite buffer regime. The regeneration rates of the systems we depend on, soil, water, fish, forest, atmosphere, are all below the depletion rates. The adult trees are still standing. The pumps are still running. The markets are still open. The GDP is still growing. The canopy is green. I want to end where we started, with Safa Motesharrei sitting in front of his computer at the University of Maryland, watching the simulation curves. He had built the model to answer a question that most of his colleagues in applied mathematics considered too large and too speculative to be worth asking. Can civilizational collapse be predicted mathematically? He found that it could. Not the timing, not the specific trigger, but the regime, the parameter space that produces collapse versus the parameter space that produces sustainability. He mapped the boundary between them. He published the map. He showed that collapse can be avoided if two conditions are met. Reduce the depletion rate, reduce the inequality, both simultaneously, before the resource base crosses the irreversibility threshold. The conditions are clear. The math is unambiguous. The paper has been cited hundreds of times, and the policy response has been effectively zero. The response was a NASA press release saying, "We do not endorse this paper." The response was the economics profession continuing to teach that growth can continue indefinitely on a finite planet. The response was the policy apparatus continuing to use discount rates that mathematically eliminate the future from present calculations. The response was the elite buffer doing exactly what the model says the elite buffer does, insulating the decision makers from the feedback that would force them to act. The model predicted its own reception. That is either the most elegant confirmation of a mathematical theory or the most devastating one. I have not yet decided which. Donella Meadows died at 59 before she saw her work validated. The economists who ridiculed her are in the textbooks. Her data is in the journals. And the curves she projected in 1972 continue to match observed reality through 2020, 50 years of quiet, relentless confirmation that nobody with the power to act has acted on. I keep thinking about the Rapanui word for the Moai platforms. Ahu. The Ahu were built at the boundary between land and sea, facing inland, the Moai on their backs gazing over the communities they protected, the ancestors watching, the dead looking after the living. Every Ahu was a statement that the past and the present were connected, that the decisions of one generation would be felt by the next, that the community existed across time, not just across space. When the Moai were toppled, when the Ahu were abandoned, when the Birdman cult replaced ancestral authority with annual combat, what died was not just a religion. What died was the institutional mechanism by which the Rapanui connected present decisions to future consequences. The Moai were, in a sense, the opposite of a discount rate. They were a structure that said the future matters as much as the present, that your ancestors are watching, that your descendants will judge. When those structures fell, the time horizon of decision-making collapsed to the immediate, to this season, this harvest, this meal, and the mathematics of a system with a collapsed time horizon is the mathematics of depletion. We have our own Ahu, our own structures that are supposed to connect present decisions to future consequences. Constitutions, international treaties, scientific advisory boards, regulatory agencies, the Clean Air Act, the Endangered Species Act, the Paris Agreement, the IPCC assessment cycle. Each one was built to be an institutional moai, a structure that forces the present to reckon with the future, that encodes the principle that decisions made today have consequences that extend beyond the decision maker's lifetime. Each one was an attempt to extend the time horizon of collective decision making beyond the quarterly earnings report, beyond the discount rate, and one by one they are being toppled, not by warriors, by budget cuts, by political appointments designed to weaken enforcement, by trade agreements that override environmental protections, by the relentless pressure of quarterly earnings expectations on institutions that were designed to think in decades, by the argument that regulation is too expensive, that economic growth must come first, that the costs of action exceed the benefits when benefits are discounted at 5% per year. The discount rate is the intellectual tool with which we topple our own ahu. We do it with spreadsheets instead of ropes. The moai fall just the same, and the seeds are being eaten, one by one, on 10,000 ordinary Tuesdays, by 8 billion people who need firewood, who need dinner, who need to feed their children, who are making the same rational, individual, mathematically predictable decision that was made on a 163 square kilometer island 800 years ago. The person cutting the last tree does not know it is the last tree. They never do. The equations do not need your permission to execute. They are already running.